This example will show a little different perspective. In it, we're going to imagine that we have this big batch of colored rods, and they come in 3 lengths: 1 inch, 2 inch, and 3 inches. So just this little wooden rods, imagine that. The 1 inch rods come in 3 different colors. So the 1 inchers come in 3 colors. The 2 inch rods come in 2 colors, and the 3 inch rods come in 2 colors. So what we're going to think about is how many different ways can you lay them end to end and create what I'm going to just call a segment here to have a word for it, but a linear arrangement of the rods of a certain length. How many different rods or arrangements like that, or segments, can we create of length n? Now, I put length 10 down here just to have a number to think about. So let me draw one of these just so you can see what I'm talking about. So we might have something that looks like this, where we have a 2 inch rod here, and then maybe it's blue like I've shaded here, and then maybe we have a 1 inch rod. That's a little long for 1 inch, I guess. 1 inch rod right here. So you have to use your imagination big time, right, to think about this. As and there's a 3 inch rod. That one turns out to be green or red. And maybe there's another 1 inch rod that comes after that, but this one is black. Another 1 inch rod like that. So that's a segment of length 2 plus 1 is 3, then 3 is 6, 7. So here n is 7. That's a segment of length 7. So there are various segments of length 7 that you could imagine from these rods as well. We're going to do this very much like we did the others by saying, okay, what's the first rod we put down, say from the left as we move to the right, both in terms of its length and its color. Now, we don't have to specify the 3 colors, but we better bear in mind that there are 3 colors. And so as we set this up, what I'm going to be right here, say, I'm going to say the color, let's see, let's do color and length, and then what remains in terms of the length of it, because we're doing this in terms of the length. AN is the number of different segments of length n that can be created. All right, so what remains, and then how many ways to finish that off. That's the word ways. Hard to read. Let me try again. Right. So there are 3 colors of the 1 inchers. So I'll just put a number 3 here, just to bear in mind that there are 3 of these. There remains now of length n. I've used 1 inch. So there remains n minus 1 inches. And if an is the number of ways that we can create a segment of length n, then this would be an minus 1 ways to create what remains. But I'm going to change this, how many each, and then put a total over here. So for each of the colors, there'd be an minus 1 that remains, but there are 3 colors, so it's 3 times an minus 1 ways that we can start with a 1 inch segment. And then let's do for the 2 inch segment, there are 2 colors, and n minus 2 inches remain. And for each of the ways we put down a 2 inch segment to start it, or our rod, there are an minus 2 ways to complete the segment. So there's 2 ways to pick the 2 inch rod, and an minus 2 ways to complete the whole segment. In the same way, if we have a 3 inch rod, there are 2 colors. Having put down a 3 inch rod, there are n minus 3 inches that remain, and there are n minus 3 ways to complete a segment. But there are 2 ways to choose a 3-inch rod color, and then n minus 3 ways to complete the rod. So in this case here, n is equal to 3 times n minus 1 plus 2 times n minus 2 plus 2 times n minus 3. The initial conditions are a little more intricate this time. They're not horrible, but they take a little more work. So A1 isn't too bad. You can think about that one for just a second, and hopefully you pause it if you need to, and then write down something. There are 3 different colors for 1 inch length, so there are 3 ways to have a segment of length 1 because of the 3 different colors. Now length 2, it already gets a little more complicated there. Because of length 2, we could have 2 1-inch lengths. So we could say the colors here are ABC. So we could have any for a 1 inch like so. There are 3 choices for the first one and 3 for the second one, right? It could be the same color. So this is a slot argument, gives us 9 ways for a 1 And then the other way is just to have a length 2. So this is a 2-inch length, and there are 2 ways to do that. So there's a total of 11. That's 11. Now A3, one can do in a similar way. I don't think I'll go through the whole detail of this. I think I'll go ahead and write down the answer here. And let's just think about it a little bit. For length 3, it could be a 1 1 1. These are all inches. And that would be 3 times 3 times 3, or 27 ways to do that. Or it could be a 1 2, or a 2 1. A 1 2 or a 2 1. And since there are 3 1 inches and 2 2 inches, that'd be 6 for each of these 2 things here. Total of 12, like so. And then finally there are 2 if it's a 3-incher, and if you take those, that's 41 different ways. It is 41. 41 is A3. So I asked you for A10. Well, that'd be crazy to try to get that. I did work it out in Mathematica. A10 actually turns out to be 380,615. Like so. All right, so one more example, just to give you a little bit more work or experience with these. There are some of these in the exam review. This one asks, how many different regions can n straight lines subdivide a plane? So if you take a plane, infinite plane, and you draw one straight line, it subdivides it into 2 regions. And so the question is, what if you have n straight lines? What's the largest number of regions it could divide it? So it will vary depending on the particular lines, but there is a maximum number we could get. So if we start off with this, we'd have, well, if there's 1, that just gives us 2. A1 equals 2. And if we have 2 of them, they could be parallel. That would divide it into 3, but if they're not, that would divide it into 4. And so that's the largest we could get right there. Now here's the idea. If we take a third line, the third line basically is going from infinity and then crossing the lines as possible, and then back to infinity, on the other side. So from infinity to here, if you imagine that going all the way here, it actually subdivides this region here into 2 regions. So we've added 1. And then from here to the next line, between those 2 intersections, so again, we've divided this region into 2. We've added a new region, in other words. We're not going to divide every region, but we have divided those 2 regions, adding 2. So thinking of infinity as a point way out here, to this intersection we get 1. And then between these 2 points you get 1. And then again, all the way out to infinity here, From that intersection to this one, we get another one. So when we added a new line to a third line, then we created 3 new regions. We added to the total 3 regions. And in fact, that's the way it's going to work in general. So for example, if we think about taking a 4th line, it may actually cross some of these, this one bounded region, right? It could do something like this. But the same thing is true in the sense that from infinity to here, it added a region. Between these 2 intersections, it took 1 region and made it 2. Between these 2 intersections here, it took this big region here, all of this right here, and made it 2, created that new little bounded region. And then from here to infinity, it took this region here and made it 2 and created another one. So there were 3 lines it could cross, and that would give us a total of 4 new regions. And that's the way it's going to work in general. If we cross again, we'll cross 4 lines maximum, like so, and that didn't cross 4, never mind. We would cross 4 lines maximum, and each time we go from infinity to a crossing, or from a crossing to a crossing, we create a new region. With 4 lines to cross, that would give us 5 regions, 5 new regions. So in fact, what we get is this recurrence relation here. AN is AN minus 1 plus N new regions. Each time we do that, we get N new regions. NA1 is 2. Right? With 1 line, you get 2 regions. So this can actually be solved, and I'll write down the solution. You could get the solution pretty easily using the techniques that we have. Basically, we have that the homogeneous part is just going to be a constant alpha because r is equal to 1, and the particular part will be an arbitrary 1st degree polynomial, but because r is 1 with multiplicity 1, we have to multiply this by n to the 1st power, so we get an plus bn squared. So that's what that would look like there, and then going through our whole process, what we come up with is a solution. An is equal to n times n plus 1 over 2 plus 1. I won't go through that whole solution, but you might use that as a practice problem for a non-homogeneous recurrence relation where you have to worry about including a power of n in there as well. And we will stop there.